Hello and welcome back. Today on the bench we've got a load of capacitors, as you can see, 4 bridge rectifiers, and all this is to make a 1000 volt power supply so that we can test the 805 power triodes that I previewed in a previous video. We're going to do the same old sort of thing that I've done before, which is to stack several high voltage power supplies on top of one another, and to power it all we're going to use a big Tektronix 545B oscilloscope transformer. Before I get into the details though, there are a few things that we need to do before I can bung it all together. These capacitors are new old stock, meaning they haven't had any power applied to them, I don't know, for probably 50 years. So before we can use them properly we need to test them for leakage, but more than anything we need to reform them. A capacitor like this, an electrolytic capacitor, it's basically like a big coil of tin foil, let's say, metallic foil, and in between that tin foil is what is called an electrolytic, and it's like a sort of chemical, it's some sort of absorbent material soaked in a chemical that enables a high transfer of electrons between the two plates of the capacitor. Over time that dries out, and these are essentially a bit like a battery, but not exactly. So we need to apply a voltage at a lower working voltage than these are used at, which is 400 volts in this case, and slowly apply that voltage, current limited voltage, so that they can reform gently and so that they don't go bang. To reform them and to make sure they're not leaking too much, I'm using a pretty simple setup. This little box of tricks here is essentially a voltage doubler, which takes the voltage from my variac, doubles it, and then we've just got a few resistors, capacitor and a neon lamp. The neon lamp indicates if the capacitor is leaking too much by shining. It should shine at first and then blink a little and then go out. There's also a resistor in there to limit the current going into these capacitors. Over here we're going to be monitoring the voltage at first and the current. So these are 400 volt capacitors. So let's start off something simple. Right, and as you can see the neon there is glowing, meaning it's leaking. And if we look over here, this is the voltage and it's going up, and this is the current going into the capacitor. At the moment this is indicating 1.3 milliamps, which is too much for an electrolytic. Oh, and I just missed that. We just turn that up again. As you can see, that neon is flashing. So I'm going to apply 100 volts ish at first, and at the moment that is telling us that there is 160 microamps going into the capacitor. That should come down over time. I won't go into great detail about reforming capacitors. This video will be too long if I did. But essentially what we're doing, as mentioned, we're putting a voltage across the capacitor, limiting the current, and as it reforms, this reading will go down. This is about 10 minutes later, and the current going into the capacitor is about 12. Oh, I don't know, seems to be going down now. It's very changeable, but as you can see, that's about 2 microamps, which is a fair reading for an electrolytical capacitor. So now I'm going to up the voltage a bit. Sometimes this can take hours or even days. This is the next day now, and as you can see, I wired up all the 3 capacitors that I hadn't reformed after reforming this one in parallel to try and speed up the reforming process. So I think I finished up about 8 o'clock last night. So there's a voltmeter. But you can see that we've got 208. We've got 228 volts. It'll read the same thing because they're all in parallel. You just check this other one. Rather do this with a big probe, so I'll try and keep my fingers out of the way. Yeah, and that's got 205 volts. So this is why we put resistors across the capacitors to bleed them off, and also to share the voltage between them equally. So when you're mucking about with capacitors, you need one of these, which is essentially a couple of bits of thick copper, a bit of wire, and a big resistor in there to bleed the current off, because the buggers can bite you when you least expect. Right, so when I do this, you'll see it will go down. You'll see like that the voltage starts increasing as well. There's nothing connected to that apart from that meter. So where the hell is that voltage coming from? And this is what they do. So as you can see there, we've got 0 volts. And there we go. Starting to increase in voltage again. Starting to, you know, there's electrons and a charge there. And that's the electrolytic stuff that, you know, stores those electrons. So I forget the correct term, but it's a thing. So capacitors, you have to watch the buggers. So what I'm going to do next, I'm going to get rid of all this gubbins. I'm going to apply another voltage to them, and then we're going to actually build the power supply proper, and we'll get into some detail. And just to prove that, like, capacitors can give you a good bout even after the power has been, you know, not applied for quite some time. Should see a spark. So that's why you need a discharge wand, discharge thingy doodah. This essentially is what I'm going to build. So we've got 4 windings from the mains transformer, one at 226, one at 195, one at 180, and one at 137 volts RMS AC. Followed by, we're going to have to put some fusing in there, followed by a bridge rectifier, and followed by our capacitors. What I'm also going to do to make this a little bit safer, because a 1000 volt power supply capable of delivering about half an amp will kill you stone dead. So to try and, you know, introduce a little bit of safety, we're going to be putting a resistor across all of these, just to allow them to bleed off, although the valve should, you know, bleed them off really, but yeah, you've got to be safe. This is the triode that we're going to be testing. So we've got another transformer to provide the 10 volts AC at, it's about 4 amps. It's getting on for 4 amps to power these buggers. Ideally, if we were running this in a proper amp, we would like a centre tapped transformer. I tried to wind one on an old toroid and everything, but it just couldn't hack it. And then the last thing we're going to need is we're going to need some sort of minus, well, we're going to need a voltage source across the control grid there. These big transmitting valves essentially work in positive grid current situations. To get the full power out of them, you need to drive that grid positive. So we need to be able to flip that voltage, but we'll get into that bit in a minute. Another day, another dollar, as they say. And here's the 1000 volt power supply all knocked up. As you can see, it's all pretty sort of bodged together. Now, obviously messing around with 1000 volts, like capable of delivering half an amp plus, is not a trivial thing to do. And a lot of people will look at this and think, oh my fucking giddy good night, you know, that's bloody lethal. However, I built this, I know what I'm doing, and I feel comfortable with a setup like this. If I was to build this properly, I would take a lot more time and effort to make it look better and not be knocked to, you know, a better standard. However, this is only going to be a short test, so I wanted to knock something together that was quick, safe, and I felt, you know, would do the job. I've got this connected to my Variac, and at the moment all of these capacitors here are isolated from one another, so they're not connected up to give 1000 volts. At first I'm only applying something like 100 volts mains AC, and I'm just going to point you at that there and try and get that in frame. So we just test the first one. So I've got it on a lamp limiter, as I said, and a Variac, so we're not going to get the full potential. And the first one measures 142 volts. The leads get entangled here. Second one 112. Third one 122. Got to be really careful with this. 86. Next I'm going to connect them all together, and then we're going to see if we can get 1000 volts out of it. Everything's connected together. Let's see how much voltage we can get out of this. We're still on part of the lamp limiter. 500 volts, 600, 700. Sorry, I keep going. Just the old back's getting me jet. Right, we've got 200 volts AC mains. $900 volts. Storm outside. Okie dokie. 960. Let's take it off the lamp limiter. There we go. Just pop that down a bit. 1000 volts ish. So we'll let that fall. Next we've got to sort out the bias supply. Well, the storm rages outside. I've knocked up a bias supply which is adjusted by this pot. As you can see there, that is reading minus 130, and we can adjust that down to 0 but we don't want to do that, so I'm going to have to put a resistor on here so that it can't at first go all the way to 0 volts on the grid. There we are, yet another day. It's taken about a week to throw all this together in between the sort of family commitments and whatnot. Where are we? We've made the 1000 volt supply to supply the valve. We've knocked up, we just wired it up, or we will wire it up to the heater supply, although it's not a heater, it's a filament. What's the difference? These big triodes have what is called a hot cathode. The cathode is made of tungsten and is impregnated, although I'm not quite sure if that's the correct term, with thorium, which is radioactive. A hot cathode, which is basically like, think of it like the filament in a old-fashioned light bulb, is heated directly with the thorium in there. That releases a lot of electrons, which when a positive voltage is applied to the anode, obviously current flows, etc., controlled by the control grid. The filament in these valves can reach is heated to about 2500 degrees centigrade. A hot cathode has a higher power density, so basically it gives off more electrons and are longer lived than an indirectly heated cathode, which you find in such valves as the ECC83, EL34, etc. A lot of people have got quite a thing about these thoriate. Right, it's a bit hard to get your head around, especially on Christmas Day. A lot of people have got a real thing about these thoriated tungsten filament valves, to the point where they will make an amplifier with valves, tubes, whatever you like to call them, with those hot cathodes. Anyway, the other thing that is really interesting about this 805 valve, what I've been able to find out, there's not a lot of information out there. As far as I know, these things were made in about 1936. You see this big block here? Hold on, let me zoom you in. What the fuck? Right, you see this big block here? This is the anode. This is made out of graphite, and it's actually made from a block of graphite and milled like in a machine to get that shape. So imagine the engineering that's gone into that. As you can also see, we've got these heavy ceramic sort of supports here that hold all the elements of the valve together. It really is a beautiful, well engineered device, because you have to realize that these things, all this expands as it's heated up. When I actually power the filament, you'll see how hot the buggers get. It's more like a light bulb. It's like a light bulb on steroids with a control grid. Anyway, bit more information to throw your way. Yeah, the anode's milled from a solid block of graphite, and as I said, there's not a lot of information out there on these. From what I've been able to find out on the Valve Museum site, this 805 Triode is believed to be a direct ancestor of the TT10 and 813 transmitting valves, which, as I've mentioned previously, are beam tetrodes. By about -100 volts up to about -6 volts. the other problem with testing these things is that if you look at most volt data sheets, it will give you a graph telling you the plate or the anode voltage compared to the anode current. In this case, all I've got is a plate voltage versus control grid current. So I don't know what to test this at what voltages or whatever. All I know is that this has a maximum dissipation of 125 watts, so therefore if we bang like 1000 volts across it, then we don't want to exceed 125 milliwatts anode current. Right, let's test this bugger. It's taken this long, about a week, to get here. I've just sort of had a bit of a quick test. So first off, let's whack the filament current on, and as you can see, these glow really brightly. I can't get the meter in that shows the control grid voltage, so I'm going to have to call that out. I've got the anode voltage. This is reading anode voltage, this is reading anode current. I've also got a meter just off shot that is showing me the voltage across the resistor that's going into the control grid, because as I've mentioned, these things run with positive grid voltage, and from what the little I can glean, we don't want to exceed 40 milliamps. So we've got about 600 volts anode voltage, and as you can see there, we're reading 0.3 volts anode current. I'm going to turn the control grid voltage down. Sorry, I'm going to try and think of loads of shit here, so if I'm a bit hesitant in my description, forgive me. As I decrease the bias voltage to the control grid, that voltage there, the reading there, should go down, and this one should go up, because as the valve starts pulling more current, obviously it's presenting a higher current draw on the power supply. So we're reading 2 millivolts, and this is at minus 18 volts on the control grid. And now down to minus 15, still only got 7 milliamps. I'm having to really feel my way here. So, right, we've got 900 volts on the anode, minus 15 volts on the control grid. We're reading 12 milliamps. I'm decreasing the control grid. Now, what I'm really worried about, because these valves haven't been powered for quite a while, and what I've found is when testing some valves, they'll suddenly go into really high current draw, they'll slam shut, as it were, you know, like a direct short if you're not careful. So we're now reading minus 10 volts on the control grid. Increasing that to about 1 kilovolt. Right, I don't know what's going to happen here, so we're now reading minus 7 volts on the control grid. We don't want to exceed 125, so we're still safe. Now we're now down to -4 volts. Ordinarily, if this was something like a 813 valve, this would be pulling a hell of a lot more current. We're down to -1 volt, no, about -2 volts on the control grid, and we're still only pulling 51 millivolts on the anode current. Shall we take it all the way to 0, shall we? Right, we're about 0 volts on the control grid, and as you can see, we're still only pulling 58 volts on the anode current. So what I'm going to do, I'm going to swap over the leads there, making this a positive voltage on the control grid. But first, let's kill that anode voltage, because I don't want to touch something with 1,000 bleeding volts on it. So I've just left the heater on. Gonna let the valve drain that voltage, that charge off those big capacitors. Right, turn the valve off. Time to get the soldering iron out and swap the leads. What I've got here is a 10 ohm resistor, and I'm using this meter to monitor the voltage across it. As soon as that goes too high, registering more than 40 milliamps, which is what? Come on. Right, let's test this bugger. It's taken this long, about a week, to get here. I've just sort of had a bit of a quick test. So first off, let's whack the filament current on, and as you can see, these glow really brightly. I can't get the meter in that shows the control grid voltage, so I'm going to have to call that out. Anode voltage, this is reading anode voltage, this is reading anode current. I've also got a meter just off shot that is showing me the voltage across the resistor that's going into the control grid, because as I've mentioned, these things run with positive grid voltage, and from what the little I can glean, we don't want to exceed 40 milliamps. So we've got about 600 volts anode voltage, and as you can see there, we're reading 0.3 volts anode current. I'm going to turn the control grid voltage down. Sorry, I'm going to try and think of loads of shit here, so if I'm a bit hesitant in my description, forgive me. As I decrease the bias voltage to the control grid, that voltage there, the reading there, should go down, and this one should go up, because as the valve starts pulling more current, obviously it's presenting a higher current draw on the power supply. So we're reading 2 millivolts, and this is at -18 volts on the control grid. I'm now down to -15, still only got 7 milliamps. I'm having to really feel my way here. So, right, we've got 900 volts on the anode, -15 volts on the control grid. We're reading 12 milliamps. I'm decreasing the control grid. Now what I'm really worried about, because these valves haven't been powered for quite a while, and what I've found is when testing some valves they'll suddenly go into really high current diode or slam shut, as it were, you know, like a direct short if you're not careful. So we're now reading minus 10 volts on the control grid. Increasing that to about 1 kilovolt. Right, I don't know what's going to happen here, so we're now reading minus 7 volts on the control grid. We don't want to exceed 125, so we're still safe. Now we're now down to minus 4 volts. Ordinarily, if this was something like a 813 valve, this would be pulling a hell of a lot more current. We're down to minus 1 volt, no, about minus 2 volts on the control grid, and we're still only pulling 51 millivolts on the anode current. We'll take it all the way to 0, shall we? Right, we're about 0 volts on the control grid, and as you can see we're still only pulling 58 volts on the anode current. So what I'm going to do, I'm going to swap over the leads there, making this a positive voltage on the control grid. But first let's kill that anode voltage, because I don't want to touch something with 1,000 bleeding volts on it. So I've just left the heater on. Gonna let the valve drain that voltage, that charge off those big capacitors. Right, turn the valve off. Time to get the soldering iron out and swap the leads. Right, just have to have a bit of an adjustment there. Right, filament voltage is on. We're at 0 volts on the control grid. Bugger all on the anode. So we're at 330 odd volts on the anode, 16 volts on the anode, 16 milliamps. Obviously I don't want to crank this right up and keep it at that, because in an amplifier, or if it was in a transmitter, it wouldn't be full on like this all the time. We'd have obviously a AC waveform going through it, so which is going off, on, off, on. Right, 600 volts, 7, 800, 900, let's call that 1000 volts. And we've got 0 volts on the control grid, 59, yeah, let's call that 59 milliamps. Increasing the control grid voltage. Right, 1000 volts, 45. Okay, I'm increasing the bias on the control grid, and that's going down, which is very strange. Okay, we have a puzzler. About 1000 volts on the anode, we've got 0 volts on the control grid, and we have about 60 milliamps going through the valve. If I increase the control grid, make it more positive, the valve should conduct more. So I've now got to about 5 volts on the control grid, and as you can see the current is going down. Why? I have a suspicion, but I think I will leave that explanation for another day after I've done a bit more testing. So this has been a bit this has been a bit of a long-winded video getting nowhere essentially. However, sorry about that. It's a bit of a long time getting up there, and it's turned out to be a bit of a wet fart, hasn't it, really? I think I know why the anode current of the valve is going down when it should be going up. I have a suspicion. I'll have to test that theory out. However, while we've got this big high voltage power supply, let's torch a few valves. This is a 6080 double triode, doesn't test very well. Let's see how it likes 1000 volts up its arse. We can do a similar thing on this ECC 88. I'm going to cut it there because it's already a bleeding long video. Thank you very much for watching. Take care of yourselves. Ta-da for now.